Mathematics has always been a field filled with elegance, logic, and patterns. Yet hidden among its beauty are problems so deceptively simple that they become traps for even the greatest minds. There is one such problem that has haunted mathematicians for nearly a century. It looks harmless at first glance, something you could explain to a child in just a few seconds. And yet, once you step inside, it consumes you. Careers have been derailed, warnings have been whispered, and legends have declared that the world is simply not yet ripe enough to solve it. This problem is the Collatz Conjecture, known by some as the most dangerous puzzle in mathematics. So what makes this seemingly innocent riddle so terrifying? The rules are almost laughably straightforward. Take any positive number. If it's odd, multiply it by 3 and add 1. If it's even, divide it by 2. That's it. No hidden complexities, no advanced formulas, just 2 little rules. And yet, from these 2 rules, a storm of unpredictability emerges. Numbers leap upward, crash down, twist and tumble like hailstones caught in a thundercloud. But no matter how wild the journey, every tested number so far eventually falls into the same endless cycle, 4, 2, 1, over and over again. At first, this might sound like a neat party trick. But here's the catch. No one on Earth can prove it always works. Millions, no, quintillions of numbers have been tested by computers. They all end in 4, 2, 1. And yet, a formal proof, a definitive explanation, continues to evade the sharpest mathematical minds. It's as though nature has written a riddle so simple that anyone can understand it, but so deep that no one can fully unlock it. Consider the number 27. It looks small, harmless, insignificant. But when thrown into the Collatz machine, it doesn't behave like its neighbors. Instead, it soars up to the astonishing height of 9,232 before finally tumbling back down to the familiar 4-2-1 loop. That one tiny number takes 111 steps before surrendering. Imagine watching other numbers around it drop quickly while 27 stubbornly climbs mountains as tall as Everest before it finally admits defeat. That kind of chaotic path raises an unsettling question. What if there's a number out there that never falls? This is where mathematicians begin to sweat. Because if even one number exists that refuses to return to 1, the entire conjecture collapses. One rebellious number could disprove nearly a century of belief. And what's worse, we might never find it. Why? Because while we've tested numbers up to 268, an unfathomable 295 quintillion cases, that's still practically nothing compared to infinity. It's like dipping a teaspoon into the ocean and declaring you've searched the whole sea. Somewhere out there could be a number that breaks the rules, a number that grows endlessly instead of shrinking. And if it exists, it will remain hidden unless we stumble upon it. But here's where the mystery deepens further. On the negative side of the number line, the Collatz rules produce not 1, not 2, but 3 separate cycles. So why would negative numbers allow multiple loops while positive numbers, so far, collapse into just 1? The universe is hinting at something deeper, something we don't yet understand. Great minds have tried to crack this riddle. Paul Erdos himself, one of the most prolific mathematicians in history, dismissed it with a warning. Mathematics is not yet ripe enough for such questions. His advice to young mathematicians was simple: don't waste your career here. Entirely brilliant minds have been trapped inside this puzzle, chasing shadows, producing no real progress, while their peers moved on to fields that rewarded them with breakthroughs and recognition. To admit you're working on Collatz in academic circles is almost taboo, a red flag that you've lost your way. And yet, the temptation remains irresistible. It is the mathematical equivalent of a siren's song. You know it may destroy you, but you cannot look away. After all, how could something so simple resist being solved? Some see in it the randomness of nature itself. The up and down journey of numbers resembles stock market graphs, on bad days, chaotic but following hidden statistical rules. In fact, researchers found that Collatz sequences mimic geometric Brownian motion, the same randomness used to model stock prices. Others noticed that the leading digits of Collatz numbers follow Benford's law, the same strange pattern that emerges in everything from population data to financial audits. Why should a playful number game echo the fingerprints of our chaotic world? And still, the ultimate question remains untouched. Will all numbers return to 1? Terry Tao, one of the most brilliant mathematicians alive, brought us closer than anyone else. In 2019, he proved that almost all numbers shrink under Collatz's rules. That's astonishing progress. But almost all isn't the same as all. Just as almost all numbers aren't perfect squares, but we know an infinite number of squares exist, it's entirely possible that some hidden sequence escapes Collatz's grip forever. Tao himself admitted his result might be as close as humanity can get without solving it outright. If that's the case, then Collatz isn't just unsolved. It might be unsolvable. John Conway even showed that certain generalizations of Collatz can simulate a Turing machine, meaning they fall under the shadow of the halting problem, questions that are fundamentally undecidable. That possibility hangs over Collatz like a cloud. Maybe we will never know. And that, perhaps, is the true beauty of the conjecture. A child can understand it, yet the world's greatest mathematicians may never solve it. It is simple enough to play with, yet profound enough to expose the limits of human knowledge. Every number we test, every graph we draw, every proof we attempt, only deepens the mystery. Think about it. From two tiny rules, divide by 2 if even, multiply by 3, and add 1 if odd, comes a universe of chaos, beauty, and impossibility. This is mathematics stripped bare. It's not about solving for X or memorizing formulas. It's about staring into the heart of order and chaos, about realizing that the smallest puzzle can contain the deepest truths. So, what if somewhere, hidden beyond the numbers we've checked, lies a sequence that climbs forever? What if buried in infinity is a loop that doesn't touch 4, 2, 1? Or what if, instead, the conjecture is true and all roads lead to one, but no human mind will ever be clever enough to prove it? That is why the Collatz Conjecture refuses to die. It taunts us, it humbles us, and it whispers a secret that maybe, just maybe, some questions are beyond us. And that truth, that mathematics itself can hide mysteries so deep we may never unravel them, is what makes this the most dangerous problem in mathematics.